Howdy. I've been looking at the Lake Pontchartrain Causeway, which is the longest bridge in the world, and it's in Louisiana. 24-mile long bridge. So I wanted to see how they um, worked out the curvature building this bridge, because in 24 miles they should have to deal with 384 feet of curvature. And I even looked at a documentary from Modern Marvels that 45 minutes long, but they finally got to the point, and it was this. They threw this up as they were going to a commercial, and it was 35 minutes in. So I barely caught it, but this is what they're to compensate for the curvature of the Earth. The Lake Pontchartrain Causeway was built roughly 2 inches longer than the distance it spans. 2 inches for 384 feet. Then I just started checking out some other bridges. This is the top 10 bridges. Our top 10 longest bridges. You can see it's not far behind Lake Pontchartrain, the next one. And there's, they're all above 100 so far, now I'm just dipping under. And then, yeah, look at this one. This one, Lisbon's Vasco da Gama Bridge, is 56,381 feet, 10.7 miles. So that is 76 feet of curvature that you should see, 76 feet of drop. So that's about a fifth of what the Lake Pontchartrain drop is, 384. So if Lake Pontchartrain just had to use 2 inches of extra road, these guys probably didn't have to use hardly any to cover that whole 76 feet of drop. And I thought I'd show you guys how I'm figuring out how much curvature we should be seeing. So in the first mile you get 8 inches of drop. So for the Lake Pontchartrain Causeway, we'll take 24 squared times that 8 inches, and then you can divide it by 12 to get your feet, and that's 384 feet of curvature that they should have to deal with, but they only had to add 2 inches of road for that. So okay, that's been explained. Now back to work. Thanks for tuning in.
Earth's energy balance will enable you to understand radiative equilibrium. You will also be able to recognize that the temperature of Earth depends on the amount of solar energy that it absorbs. The temperature of Earth depends largely on the total radiation received from the Sun. The Earth reflects about 30% of the solar energy radiation reaching it and absorbs the remaining 70%. The absorbed solar radiation heats up the Earth. While the Earth continually absorbs solar radiation, it will not simply continue to heat up. In response to this heating, the Earth emits long-wave radiation into space. The emission of long-wave radiation cools the Earth. As the Earth cools, it emits less radiation to space, but because it is still continually absorbing solar radiation, it still heats up. As it heats up, the Earth emits more radiation to space, and so it cools. This dynamic physical process of absorption and emission and resultant heating and cooling creates what is known as a state of equilibrium. The term equilibrium describes a stable condition where all of the influencing factors are in balance and so cancel each other out. Because of this equilibrium, the temperature of the Earth has been relatively constant over time. For scientists, this balance between the amount of solar radiation absorbed and the amount of long-wave radiation emitted by the Earth is known as radiative equilibrium. Radiative equilibrium tells us that the long-wave radiation emitted by the Earth will equal the amount of solar radiation that is absorbed by the Earth. In fact, we can determine the temperature of the Earth by knowing the amount of long-wave radiation it emits. If one of the components of the Earth's energy balance changes the amount of long-wave radiation the Earth emits, the temperature of the Earth will also change, and the Earth will arrive at a new radiative equilibrium. For example, if the amount of solar radiation absorbed were to suddenly increase, the amount of long-wave radiation emitted would also increase. The temperature of the Earth would then increase, but a new radiative equilibrium would be reached, so the Earth would not continue to become hotter. In summary, the Earth's radiative equilibrium describes the balance between the incoming shortwave and the outgoing long-wave radiation. The temperature of the Earth can be determined by the amount of outgoing long-wave radiation, which is equal to the amount of incoming solar radiation absorbed by the Earth.